Hi everyone. We're going to have a look at sample U now. When we test sample U for unsaturation using the bromine water test, the orange colour remains. And this means that we don't have any multiple bonds in our compound, such as a double or triple bond, which means we can rule out having an alkene or an alkyne functional group. When we do the oxidation test, the orange colour also remains, and this means that no oxidation has taken place, which means we can rule out having a primary or secondary alcohol as a functional group or an aldehyde. So remember, that means that we can still have an oxygen in our molecule, and we can still consider the functional group could perhaps be an ether, an ester, an amide, or a ketone. Or it could be a carboxylic acid. But when we do the carboxylic acid test, we don't get any bubbles. So that means that we don't have a carboxylic acid functional group. Having a quick look at the IR, remember that we usually want to have a look at this above the 1500 region, because below there is the fingerprint region. So we'll have a quick look above the 1500 range. And already we can see a couple of signals are coming to light. So for instance, the first signal we have at about 1600, we're seeing here this rather broad signal. It's a little bit lower than we would potentially expect for a carbonyl group, so that's a carbon with a doubly bonded oxygen. The tables say above 1680, and this is about 1600, but I'm going to pop it in there because it is coming up, and so we don't want to dismiss it. Keep an eye on that there. And then we move up to this very familiar signal just below 3000, which obviously is due to our CH vibrations. And then we have this interesting signal here that has two peaks, and that is sitting at about, let's say 3000, about 3350. And so this could be an NH vibration. So here we could be looking at an amine, or if this is a carbonyl signal down here, we could be looking at an amide. So that's something to keep in mind. And so the next thing will be to see if we do have an oxygen in our mass spectrum. So keep in mind here, we're not 100% sure about this one here. We've identified it as just outside the carbonyl region, but we'll keep it in mind. Next, we have a look at our carbon-13 NMR, and we can see we have three peaks of the same size. So we're going to tentatively say that maybe we have three carbons in our molecular formula. And then we move to our proton NMR, and from our proton NMR we just want to find out how many protons we might have in our sample. So here we see the integrations in green. So we have 2, 4, 6. We probably have 9 hydrogens in our molecular formula. Keeping this in mind, we then have a look at our mass spectrum, and we have a look at our molecular ion peaks, the one that's furthest down the spectrum. And here it's sitting at about 59, and maybe we have a very small signal. 60 here, it's probably a satellite. So this being the largest signal in this part of the spectrum at around 59. If we take our 3 carbon signals and our 9 protons, this gives us a mass of 45, which means we're missing 14. And immediately this missing number, 14, is the atomic mass of nitrogen. So we probably have a nitrogen in our compound and no oxygen. So if we think back to our IR spectrum, that signal that was just below 1680 obviously wasn't a carbonyl peak, so we can rule that out. So we're looking like we potentially just have an amine in our compound. And again, just to confirm, it's not halogen. We don't have that 1-to-1 or 3-to-1 molecular ion peak we would expect to see if we had, say, a bromine or a chlorine in our molecule. Having a look at our carbon NMR, it's not going to tell us an awful lot. we can see a signal that's down at about 40. This could be due to an alcohol, ether or ester, but we've ruled out that we don't have a carbonyl group in our molecule. This could also be due to our carbon next to a nitrogen, which can come between 25 to 60 ppm. So this is probably our carbon that's next to our nitrogen, and then we have two other carbons to assign. The first thing I do when I come to my proton NMR is to draw in my carbon backbone. So we know that we have 3 carbons. And then the next thing I do is I always look at the bottom half of the region in the proton NMR. So that's below 1, because very often we see this signal here, which integrates for 3 protons and is a triplet. And that is usually indicative of a CH3 group next to a CH2 group. And it's a really easy way to start building up your molecule to identify this signal, because it means immediately I can go in and put in, whoops, that should be a hydrogen, put in my 3 hydrogens on one end of my molecule, and then the carbon right next to it I can put in 2 protons. And so I've already populated half of my structure. The next thing I need to do is to have a look for where my amine might be. So the fact that we have populated half of our molecule already indicates that my amine is probably going to be on the last carbon. So it's going to be a terminal amine. So that's the next step I can take, to put in my terminal amine. And this means that we have what is called a primary amine. So a primary amine, kind of like a primary alcohol, a primary amine is an amine that only has 1 R group attached, or 1 carbon chain, and 2 hydrogens. And then we can end up with a secondary amine, which has 2 R groups attached, and the nitrogen only has 1 hydrogen. And then we can have tertiary amines, where the nitrogen is attached to 3 different R groups or carbon groups, and we have no protons. So here, because the nitrogen is on the end, we have 2 protons, and I can look for these protons in the signal, in the range of signals. And this nitrogen here, these 2 protons can actually pop on and off. So nitrogen's a bit like oxygen, it's a bit acidic, and these hydrogens can pop on and off. And this means that it doesn't matter whether I have a primary or a secondary amine, I'm going to see a broad singlet for these signals. And obviously if it's a primary amine, they'll integrate for 2. And in here I can see this large broad signal, which we've been told integrates for 2, and that is due to my amine protons here. The only thing left is that this carbon here is missing 2 protons. So before I had 5, 6, 7, so now we've got 9 protons. And this carbon here, because it's attached to the nitrogen, will be shifted downfield, the nitrogen being a more electronegative element. And because these 2 hydrogens here are acidic, they don't count towards the splitting, or they don't affect the splitting pattern of these 2 hydrogens at this carbon that's adjacent. Which means this carbon here, which has 2 hydrogens attached, is only next to, or only affected by, these 2 protons here in this environment here. So we would expect this signal here to integrate for 2 and to be split into a triplet, which is what we see with this signal here. And then our final pattern would be these 2 hydrogens here, which are next to the CH3 group and this CH2 group, so they have 5 protons surrounding them, and therefore we would expect that signal to be a sextet. And so a sextet looks something like this. And we can sort of see in this part of the NMR spectrum that we have approximately this part of our molecule. Now we double check that we do have the right proposed structure, and we do that by just cross-correlating between all of our signals to make sure they make sense and they're what we expect to see from our proposed structure. So this CH3 group here is next to a CH2 group that has 2 hydrogens, so I would expect to see a signal upfield because it's not next to any electronegative elements, and it would integrate for 3 and it would be a triplet, and this is what we see at signal number 1. This CH2 group here is next to a carbon that has 2 hydrogens attached and a carbon that has 3 hydrogens attached, and so I would expect this to be slightly more upfield than the CH3 signal and to be a sextet, which is what we see for signal number 2. Signal number 3 is nice and broad and integrates for 2, and as we said before, these are the 2 hydrogens on the nitrogen. And then our final CH2 signal isn't affected, isn't split by these 2 hydrogens on the nitrogen. It's only split by these 2 hydrogens, so we would expect it to integrate for 2 and to be a triplet, and to be slightly more downfield because it's next to this more electronegative nitrogen. And this is what we see in signal 4. So the only thing left is to name our molecule. And we obviously have propane as our base alkane. And we want to put our amine group at the lowest number on our alkane chain. So this would come at number 1. So we would have propan 1 amine. Now imagine if we were to, for instance, move the nitrogen, the amine group, to sit in the middle and have propan 2 amine, for example here. How would we expect the signals to change? And this is just to do a second double check your initial assumptions to make sure that what we have assigned is correct. So if we moved our nitrogen to, say, sit at this group here, and so we're keeping it as a primary amine, just changing where it is, so we'll still expect to see the signal due to the nitrogen protons. That wouldn't change. But then we would have only 1 proton attached to the more carbon attached to the amine, so we would expect this to integrate for 1. And it would be surrounded by 2 CH3 groups that are in the same environment. So it would be split by 6 protons, and we would expect it to be a septet. Instead of a triplet. And then we wouldn't see this 2 protons here, and we would instead see this integrate for 6 as a doublet, not a triplet, because it would only be split by this 1 proton here. So that's just a way to double check that you have put the nitrogen in the right place. I hope that makes sense for sample U, and going through where the amine might be and what form the amine might be in as well. Is it a primary or secondary amine? I hope you found that sort of rationalisation and that stepwise process helpful.